Hello, on today's videos we'll see how to create an UV-based wet map, how to import that into a co-op network, and finally bake a texture sequence to disk. If you like this and my other videos, please consider supporting my work on Patreon. Okay, so here we are in Houdini with this very simple scene. We have just a sphere and a grid, and we are going to wet map this grid here. So, and the grid also has only one primitive, which is great for us to demonstrate the decoupling of the wet map generation from topology. So the only requirement for this to work is that this receiver geometry or the grid here has non-overlapping UVs. All right, so let's start creating a grid here, a new grid with size 1 by 1. And let's also transform that, so rotate 90 degrees in X, and let's position that 0.5 and 0.5 so we stay into this 0 to 1 unit range here. Alright, so this will be our resolution of our map. So we're going to generate a square map, so let's link rows to columns, and let's give it a little bit more resolution. Alright, so now let's create some UVs for this grid. So UV texture, and we're going to project along the z-axis, and now we need to just keep the points. So let's delete geometry but keep the points. Yeah, so okay, now here we have this vertex UV attribute, but we need this to be at the point attribute. So let's do an attribute promote, because you need to query those values down the tree. So attribute promote, and we are going to transform UV from vertex to point. Okay, great. So now we need to transfer this UV position to the 3D position using the UVs from this receiver geometry. So to do that, we're going to drop an attribute wrangle, and the points go into the first input, receiver geometry into the second input, and let me call that project points. And here we're going to make use of this UV_dis function. Okay, so UV_dis queries geometry from using the UV space. So let's create a float UV distance. UV distance will be this UV_dis function. We're querying the second geometry, so the receiver geometry, which is input number 1, and we are searching on that geometry for the attribute called UV, and the points we need to compare are the UV attributes on the point geometries. Okay, so on this geometry here. And now the last part is that we need to pass two variables so that the function fills for us, which are the primitive index and the primitive UVs. Okay, so this will search for the same UV value you have on this geometry onto this geometry, and return you the primitive index and primitive UVs, which are the values you are going to use to interpolate the attribute later on. Okay, so it's giving us errors, and that's because we have not yet declared those variables. So let's do that right now. So int prim index, so it's integer because it's the primitive index, and vector primitive UV. Okay, great. So now how to interpolate the values? We're going to set p as the prim UV. So prim UV function is going to query for a primitive and a defined UV inside that primitive for an attribute. So the geometry we're going to query is the second input or input number 1, and the attribute in this case is p because we are going to transform the points. And now we need the prim index, which we have acquired from the function below or above, prim index and prim UV. Okay, so it's trying an error. Okay, same column. Great. So this is working. And just to prove that, let's input more interesting geometry. So let's create a pig head. So those will be the receiver. And here you can see the points onto the pig head, and just to prove that, we can go to the project points and just interpolate the values. So let's create a vector position variable, and p will be the lerp, which is linear interpolation between the point itself and this position, and we are going to use a channel to control the blend. And if we change this slider, we can see the grids turning into the pig head. Okay, so that's what we are doing with the receiver geometry. Okay, so let's connect back our grid, and we don't need this pig head anymore. Okay, so now we want to do the usual stuff. We want to attribute transfer one value from the sphere to the grid and compute the wet map. All right, so for that, let's first create an attribute into the caster geometry, which is the sphere in our case. So let's attribute create. We're going to create an attribute called paint, and the value will be 1. Okay, and now we need a solver swap because we need the values to accumulate, so we need a solver for that. And now we need to connect the points onto the first input, and this paint sphere into the second input. And before diving into the solver, I just need to pin this viewport so that we don't have any update issues. Okay, so let's dive inside. And for this we need two nodes, this prep frame which holds the accumulated data, and this input 2. So we're going to attribute transfer, and the attribute is called paint. Cool, so let's check the result. And one more thing, before checking the result, let's color so that you can visualize this thing working. So let's color ramp from attribute, and the attribute is paint. Okay, so let's leave this as a visualize node, and let's go back to our solver here. And right now I can say that our distance threshold is way too big, so let's move that down a bit. Okay, so this is what I have for now. And now is the time we can just give some more resolution to our map. So let's say we need a 200 by 200 map, and we need to go back to first frame. Okay, so let's check now. Let's template the sphere, and let's check the radius here. It's too big, it's still too big. So let's go back to our attribute transfer and down the distance threshold. Okay, something like this. The last thing I want to do here is to give some fade to this wet map so it can dry. So let's create an attribute wrangle, and this will be very simple. We're just transforming the paint attribute by multiplying. So times equals 0.9. So at each frame it it removes 10% of the value. Okay, so this gives something like this. So we are drying the paint. Let's make it even slower so we have more paint going on. Okay, so something like this. And now our wet map is ready. We did two things up until now. We created this, created and projected our UV grid into this receiver geometry, and we created our wet map. Now we want to bake that to texture. All right, so we can like save like a sequence of textures so that you can use later on. And to do that, we're going to make use of 2D volumes. Okay, so volume. So we're going to check two-dimensional here, and the uniform sampling divisions will be linked to our map resolution, which we use it from these rows here. So let's copy parameter and paste relative references. And one more thing you have to change, which is you have to give your primitive field a name. So let's call that C for color, and I'm going to call that C because it matches the naming conventions from the COP network. Okay, so that is easy for us down the road. And the rank will be vector because it's a color. Okay, and now we need to transfer our map. For each voxel, we're going to map the related point from this geometry. So for that, we're going to use a volume vol. Plug volume into first input, geometry into the second input, and let's dive inside. Okay, so here what we want to do is to transform the voxel indices into a list of consecutive values so that you can match with the points. All right, so let's imagine we have these numbers in blue here are the point numbers, the point indices, and the numbers in red are the the voxel rows and columns. So we want to transform, for example, this cell 0 and 0 into this value 1 or 0, sorry, and then we want to transform this 0 and 1 into 1, and so on and so forth. This will be 2, 3, 4. So this will be like 1 and 1 and 1 to map that to 4. So basically we are transforming a table type of numbers into a linear consecutive list of numbers. All right. So very simple math. The math is we need to get the total number of columns, multiply that by the current index we are sampling, and add that the row again. All right. So for example, if you want to access this number 7 here, we have 3 columns. So 3 times 2, which is the index of the row. 3 times 2, 6, plus the number of columns, 7. So we get this number here. All right. So let's do that in Houdini. Okay, so here in the volume VOP, we have access to the cell indices, which is this IX, IY, and IZ, and the number of rows and columns, which is the res X and res Y. So the math is very simple. So we have to multiply. So multiply the number of columns. Remember, we have to multiply the number of columns by the row index. So number of columns is res X by the index from Y. Okay, so we are multiplying that, and then we need to add the column again. So now we add that. We add the EIX, which is the column. Okay, so it looks a little bit confusing, but it's very, very simple. All right. And now we want to bind export that. So bind export. And we're going to bind export that to our actually, before binding exporting, we have to check for the color attribute on the paint attribute on the input geometry, because right now what we did was just to match voxels to points. Now we need to query the attribute itself, and remember we are going to query this paint attribute here. So let's go back, and for that we can use this import point attribute, which is the way we can gain access to the attributes in the geometry. So the point number will be this value we computed here, right? So the signature is vector is vector 3, because we are going to create a color. The input, we're going to sample the second input, which is the point geometry, and the attribute will be paint. All right. And now we're going to bind export the result of that attribute into our C primitive field. All right. So this will be type vector. Okay. So what it did now is just transferring those color that we actually can already see into the UV space. So let's do one thing. So let's attribute wrangle that back to the original position. So we are going to just say that our P is again our UV. Okay, so let's check that. We have something here. All right, so now we see the wet map back into this 0 to 1 space, and we need to transfer that to this 2D volume, and we just did that using using this this kind of volume VOP. All right. And we're going to later on we're going to flip, because it as you can see it's flipped, but that's very easy to fix. We're going to do that later. And now as a last step, we need to again read those values from a COP network and just create a map from there. So let's do that right now. So before that, let me create a new here, and let's call that out volume. And let me create a COP network. Okay, so inside our COP network, we're going to import this 2D volume, and we can do that by using this SOP import node, and we can visualize that at the composite view here. So to initialize that, we need to just provide a SOP node for it. So let's provide this out volume. and then we need to set resolution and set planes from SOP. And what we'll do is to go into this tab here, and it creates this size override, which queries our volume size, and also it creates this custom plane string that reads the color for us. But the override size, we don't want to go every time and then click set resolution from SOP, so of course we're going to link that to our initial grid resolution. So let's go back again to our first grid here and just copy this parameter and paste relative references on both boxes. And now we have something that is already working. So we can see the map is transferred over to our compositor here. So we can just go back now and up the map. Let's say we want 1000 by 1000 map, and let's go back to first frame so that it can compute that again. And you can see it paints a 1K map. All right, so we have this. And remember, we have this flipped geometry here, so we just need to go to our copnet and flip that vertically. Okay, and now we can already write the map. So let's write that to disk. So file cache. Sorry, not file cache, is drop file output. And I'm going to write to any place here. Okay, let's create desktop, test, wetmap, and let's create here a wetmap dot frame dot png. All right, so let's create a wetmap from 1 to 48. So render that. And you can see it's not, it doesn't take too long. All right, and then we can go back to our initial geometry here. So let's check our grid again, make sure it has proper UVs. And now we can check the map applied. So let's create a game dev quick material. And let's load the texture. So wetmap. And there you go. So we only had one, and it's giving me a little bit some error here. I believe that's because we have some sort of solver issue here. Let me check if this frame is okay. All right, let me write that again. So render that. Okay, let me reload textures. Okay, so you see this this is already working, and it's great because you don't need to rely on topology. So yeah, you don't care about topology anymore. Then what you can do is to go to your solver, and let's visualize that again by unpinning this, or actually let's pin that to this viewport. And we can always go to this attribute transfer and just add some blend so that we have like a smoother attribute. So let's paint that and check the results. So you see it has a little bit of a smooth value here. Or you can actually go to your cop network and apply a 2D blur here. It's up to you. So you can manipulate that map with many options here. So let's regenerate that with a little bit more blur, and let's check that again on the geometry. So back to the geometry, let's visualize the quick material node, and let's update textures, and there you have it. It's a new map with some blur. Okay, so that's how you can use that, and I have created this this little HDA FC Wetmap Baker that does that for you. So in this case, we would need only the caster and receiver, so we can plug just like that. And you can visualize the preview particles, and you have many options here. You can visualize as UV, and you can also not only bake like black and white colors, but you can also use colored particles. So you can bake like that. And then this has another option, that is if your caster geometry has low subdivisions or like simple topology, you also have problems. So in this case, as we're only dealing with points, you can always scatter points on the top of your geometry over the surface or inside the volume, and then just use that as your caster geometry. Okay, so that's very like flexible way of working. So yeah, so then this has this Map Baker tab where you can set the resolution. So let's say 1K map, and I'm going to again write that to test Wetmap, and let's write again to the same place, and you can just render that and wait for that to compute. And when you're ready, you can just visualize that and update textures, and there you have it. Okay, so this small HDA will be available on my Patreon, so you can just go there and download that. Great, so I hope you enjoyed this tutorial, and I hope to see you in the next one. Until there, bye bye, take care.